Can you imagine if there was a way that we could actually recover a sample from Oumuamua, like chase down this interstellar asteroid, land a probe on it, retrieve a sample, and bring that back home to Earth? And this was a NIAC grant phase 1 concept that I brought about a year ago to your attention. And I had a really fascinating conversation with Dr. Christopher Morrison. And he has now been awarded a phase 2 grant to take this idea and explore not only if that idea is still feasible, but what are some other applications of a spacecraft that is capable of like 12 astronomical units of travel per year. What kinds of places could you go and what could you see? And some of the answers you might find kind of surprising. So now this is part 1 of a 2-part interview that I have with Christopher. In this part, we talk about the first NIAC grant, I guess the phase 2 NIAC grant. And then in part 2, we talk about a completely different NIAC grant that Christopher and his team have been awarded from NASA, which is, we'll get into that with part 2. So enjoy part 1. Well, hi, Chris. It's good to see you again.
Yeah, it's great to see you again for the second time. I'm excited to chat.
Yeah. Yeah, well, this is funny because I've been interviewing all of the people who've received NIAC grants, and I've done, I guess, such a comprehensive job at this point that now I'm getting a chance to talk to the people when they hit phase 2 and in some cases phase 3 and sort of see how the evolution of the plan has changed from the initial we've got a crazy idea that just might work to we've done a bunch of thinking and have more conclusions to bring. So let's start. And this interview is going to be a little different because we've got 2 NIAC grants that you're associated with. And so we're going to cover both of them in this one interview. So I guess let's start with the phase 2 grant, which is entitled The NICS Mission to Observe the Universe from Deep Space, enabled by Ember Core, a high specific power radioisotope electric propulsion system. And I interviewed you more than a year ago about the first iteration of this. So I guess catch people up to speed on what is the NICS mission.
Yeah, I'll start with the phase 1 and then evolve into how it turned into the NICS mission, which is, despite having a different name, it actually is a continuation from the phase 1. So the original mission was to intercept an extrasolar object. And these objects, they come from outside the solar system, and they actually come into the inner solar system, relatively close to Earth, in the Mars, Jupiter kind of area. And we saw Oumuamua as it was leaving the solar system after it had come very close to Earth. And the challenge with these objects is speed. It's not distance. They're quite close. It's speed. So unlike, let's say, a mission to the gravitational lens at 500 AU, you're only trying to travel a couple AU, and the mission is move quick, catch up with it, and then come back. And the key technology here is a radioisotope that NASA looked over, they looked at it and passed it over in the past. And the reason is it has a short half-life. A radioisotope contains about 1 million times the energy density of traditional chemical systems. So all of this energy is stored in these atoms, and the half-life determines how quickly that energy is released. So the innovation in the first NIAC was, hey, if we use a shorter half-life radioisotope, we can actually get a power density, the amount of energy per unit time, that is much, much greater than traditional plutonium. So for missions where you don't need a long duration, where you're only looking at, instead of decades, such as the missions to the Voyagers that are outside the solar system, if you only are looking at a few years or maybe 1 decade, you can have a much higher performing system because you've looked at these other isotopes. So the phase 1 focused on this particular Oumuamua intercept and sample return, and it came back with, hey, this works pretty well, especially if you have a small payload. If your payload, we looked at a 20 kilogram payload, which was about the size of the Hayabusa 2 return system that that actually recently we've gotten results from, and it was a really cool mission. And one of the things that was also missing from the phase one was the scientists. This was kind of me as a technologist going out there and saying, this is a really cool thing. And I think I can't imagine something cooler than going out and finding an extrasolar object and bringing something back. I don't know what science we're going to do. I don't know what mass spectroscopy or isotope ratios we look at and solar system formation. Those are all questions for scientists. So moving on to the next phase, this phase two, it's a continuation because it still uses the concept of fast, short missions using this high specific power radioisotope. And there's a few additional innovations. In the previous one, a lot of it was focused on spacecraft design because you have something that emits radiation. And in the NASA plutonium-238 systems, that radiation is in the form of an alpha particle, and alpha particles don't travel very far. So most of that energy is deposited locally. You don't have to worry about it interacting with your systems. But some of the isotopes we've been looking at are higher energy gamma rays as well. They're a beta emitter, which when you have radiation, it's typically alpha, beta, or gamma. And the alpha doesn't go very far. The beta doesn't go very far either. But the problem is the beta is actually an electron. A beta decay is an electron gets ejected from a nucleus, and as that electron slows down, it generates what's called Bremsstrahlung, which is breaking radiation, which then generates high energy photons that travel, a couple centimeters through really, good radiation shielding. So a lot of the innovations were focused on how do we design a spacecraft architecture that can deal with the radiation. So we came up with, put the radioisotope on one end, potentially on a boom, use electric propulsion, but use metal-based electric propulsion. There's some indium thrusters that's your shielding now. You're using your propellant as your heavy radiation shielding. There are some other innovations, such as what's called a ejectable shield, whereas you're going through the atmosphere of Earth. You have this big, hefty, multiple metric ton safety system on there. And then once you get into a high enough orbit, you eject a lot of that mass. So now you're a lightweight system and you only keep the shielding that's protecting your electronics. So you take all these innovations. And in the phase two, I wanted to add one more pretty cool piece to this, which is...
Well, sorry. So just before we get into that, I just want to give people this brief summary, because I think, there's a lot of ideas that you just sort of put in there. So just to sort of help people understand, like the gist is that you take the RTG, the kind of thing that's on Curiosity or Perseverance or Voyager, that is producing heat attached to a thermocouple, producing electricity. You swap out the plutonium for a radioactive element that is decaying a lot faster so that you get more power, and then you bolt that onto an ion thruster. And so it's really just like, I imagine like a one of those giant drag race cars, that are just all engine, right? And so this thing is just designed to just pump out electricity as fast as possible and accelerate this relatively tiny spacecraft with this miniature payload to enormous velocities, the kind of velocity that you would need to chase down a interstellar object like Oumuamua, but better than that, still have enough delta V capacity to bring that sample back home. And the idea was great. I loved it. And when last we talked, you were like, well, this is the plan, right? And now we're going to look into each one of these pieces. And so, this idea of the, I guess, more dangerous radiation comes up to the spacecraft. And that was sort of one of the issues that you had to solve. So I guess, what were the big technical issues that you were hoping to solve with the first version of the grant that you feel like you've solved now?
I think a lot of it was the integrated spacecraft design. I can go in and say, hey, we have this radioisotope. We have to be able to manufacture the radioisotope. We looked a little bit at that. We manufactured some targets, and there are a number of different ways you can obtain isotopes. You can buy some. Some are produced today, especially for medical procedures. But what we look particularly into is producing them at a reactor. So there's some work that looked into the radioisotope production. There's a lot of work that looked at the shielding, because it's fairly complex to evaluate. Hey, we're emitting all of these gamma rays. For cobalt-60, which was the main one we looked at in the phase 1, the gamma rays contain most of your energy, and they actually travel a couple centimeters before they deposit most of their energy. So looking at, how much energy is actually deposited in our block of either tungsten or uranium. And then, the heat gets deposited into this block. You have to transport the heat through a heat pipe to your power conversion system. And looking into, hey, there's thermoelectrics, which have been used extensively by NASA. Those are quite low efficiency. There's Stirling engines, but the problem with Stirling engines is that they're more sensitive to radiation. They have to have a controller. They have to have they have certain organics, such as in bearings. And usually when X-rays hit metal, it's fine, because the electrons get knocked off and they can move around. A metal's a conductor. In a organic system, if an X-ray hits it, a lot of times you create a gas. You create you separate the carbon and the oxygen from your system, and the oxygen goes and leaves, and you end up destroying your organic materials. And then with to some degree with magnets, you can actually damage the magnets. And especially with circuit boards such as silicon, you can have things that were designed to be insulators, where the electrons are supposed to be trapped, and you're knocking electrons out of them, and you're doing what's called a charge buildup, where the thing becomes more and more positively charged. So, looking at, okay, I've got the heat to my power conversion device. I have to find a power conversion device that can withstand the radiation that's hitting it. And when you're dealing with electric propulsion, a big deal is high voltage. You need high voltage to accelerate your electric propulsion propellant, typically, or sometimes a magnetic field. But you typically need kilovolts of electricity. And one of the most challenging pieces is when you have these high kilovolt materials, if they get hit by radiation, they break down. You knock an electron off, and that electron is accelerated over the voltage potential, and then it just damages and destroys your whole power conversion system. So to make this all work, there were a number of tricks that I mentioned a little bit earlier, but one of them was using your propellant as shielding. So over the bulk of the mission, you have hundreds of kilograms of propellant, and that works really well for the first large part of the mission. And then as you start to use up your propellant, it becomes a challenge. Another one was a boom. The further you put something away, the less radiation you get. So all of these pieces, they're all connected. You can't just go off in a corner and say, I've invented this magical power source and it works. It's, hey, how does that impact the spacecraft? How does the spacecraft have to change in design? You're not going to put this on a CubeSat. You're going to have something that looks very different than a CubeSat. And we ended up with a nice innovation was that the propellant tanks of liquid metal don't need to be high pressure. Liquid metal can be stored at low pressure in very, let's say, like torpedo looking tanks. They're very long, have a long aspect ratio. And that's really beneficial because you can have all this material in a really long object that's skinny and put your sensitive components behind it. And unlike xenon's pressure, you got to have a big circular tank. And if you use a big circular tank, it's not very good at being long aspect ratio and shielding things. And there are a lot of these. Another one is temperature. As you're traveling through space, your isotope is decaying. So if your mission is 10 years long, but your half-life is only 5 years, your end of life power is only going to be 25% of what it was at beginning of life. So one of the things we proposed is ejecting heat pipes as you travel. So as your spacecraft decreases, as the radioisotope loses power, you start off with 10 heat pipes, and you have a system that ejects those kind of components along with the radiator in a certain way that you keep your temperature the same. And another one is we focus mostly on solid state. We looked a little bit at Stirling's, but there are some really nice high temperature thermoelectrics out there. Usually a thermoelectric is not high temperature. On Earth, we use them for low temperature waste heat. But JPL, as well as the silicon germanium traditional radioisotope, actually work pretty well at high temperatures. But there's a little bit of a efficiency factor that, hey, I can get this thing that it's low efficiency, but it's really high temperature and radiation tolerant. Versus you look at a Stirling engine and you say, oh, well, it's highly efficient, but it's not radiation tolerant, and you can't quite use it as high of a temperature, which radiators are a big deal. If you would reject any Carnot cycle or any thermodynamic cycle, you always have waste heat. And your radiator has to be a certain size to reject that waste heat for a certain temperature. And if you go from, let's say, room temperature heat rejection to, in an absolute scale, we're at about 300 Kelvin. If you go up to 600 Kelvin heat rejection, or 300 degrees, or something like 300 degrees C, you get 16 times more efficient heat rejection per unit area, because it's T to the fourth on that. So all of these pieces have to be put together in an integrated model, and feasibility is shown by combining them. And that's kind of where the phase 1 NIAC, the initial kind of focus was on proving out the viability of a lot of these techniques. But the limitation is there's only so much money and so much time. So we went down a lot of these paths, but I'd say the phase 2 is really going to enable us to create a more integrated model that is, I'll talk when we transition to phase 2, probably here in a second. I'll tell you about how it's building upon the phase 1 in that way.
So I'm kind of envisioning in my mind, and I'm still kind of going back to this drag race vehicle, but it has a fairly long boom with multiple fuel tanks clustered around the RTG in the back, and it is somehow connected to a electric engine that's trying to keep as far away from the RTG as possible. And then you've also got your instruments, your scientific instruments, and some 20 kilogram payload, again, as far away from possible. So is it going to be this sort of very long boom, almost like a flying crane? I'm kind of imagining something that's very long, with all the parts and pieces kept far away from each other as much as possible, and yet still has, can balance its thrust down the center line of the vehicle.
Yeah, we've likened it sometimes to a dumbbell, because we've got this heavy object on one end, which is the radioisotope and shielding. I didn't mention this earlier, but the shadow shield is what that term means when you only shadow a part. You're not shielding the whole thing, you're shadowing a part. So it's heavy over here, and then you have your boom, and then you've got your fuel tanks along your boom, and then you've got your spacecraft and the other pieces. And so it does end up being a large aspect ratio spacecraft, and we've got a couple of renditions of it on the website. One of them actually doesn't look like a large aspect ratio, but that was where we have these the several tanks. There was another concept where it was a much longer aspect ratio, and I think we right where the phase 1 ended is right as we acquired some software to help us do CAD modeling to radiation. It's actually, we have these really old nuclear codes that were written, literally they're the first thing written in Fortran, and they're still kind of the state of the art. And if you want them to play well with, you're editing a text file to try to create like cubes and spheres that approximates your thing. So if you actually want hey, I've got this complex object, you really have to have a tool that can take it and turn it into a much more sophisticated model. So I'll say right at the end of the phase 1 was when if you look at the phase 1 final report, you'll see like a picture towards the very end that's like, hey, here's our proof of concept. But we kind of ran out of time to really show the let's say trade space for it.
But are we getting kind of almost close to you guys are building an Oumuamua of your own with that kind of an aspect ratio, right? Interesting.
Maybe,
right?
yeah.
All right, let's talk about phase 2. So your original plan, and this was exciting, was wouldn't it be great to chase down Oumuamua, grab a sample, bring it home so scientists can study the formation of an entirely different star system? Okay, top that.
I think I just might be able to.
Okay, I'm ready.
All right. So one of the challenges is a 20 kilogram payload. It wasn't a lot. It was 20 kilograms and 100 kilometers per second at delta V. And when you did all the math, you could say, I can put together a defendable concept that can do that. But we ran into a few astrophysicists. So one of the things that makes NIAC a NIAC is really the combination of scientist and technologist. I'm the technologist. I think of all these cool things. As I mentioned Oumuamua, I'm like, oh, it's guaranteed this is cool science if we can sample return. I don't know what the science is.
Right. Not my problem.
Yeah. The piece here is we actually ran into a few scientists. And one of them, John Artenberg, was the chief engineer of the James Webb Telescope. So he's very connected, knows all the people, and he had some really cool ideas along with some of his colleagues. And what he said, what about a telescope? Can you bring a telescope with you? And looking at it, it's like, well, a telescope, a certain size of lens, it's going to weigh more. It's going to be more than 20 kilograms. But what could you do with a telescope with this type of spacecraft architecture? So one of the coolest things is there's this dust, in the ecliptic. You have the ecliptic plane. Conservation of angular momentum means you have this dust. It's spread out, even out into the Kuiper belt. Light from the sun will shine, hit these dust particles, and bounce back and cause noise if you're trying to observe something. So there's these incredibly dark objects that it's, even if you had the biggest lens in the ever built near Earth, there's just a lot of this noise and light pollution from the ecliptic. So the goal is to get out of the ecliptic, and to get out of the ecliptic into more pristine dark space. We're talking 5 to 10 AU out of plane. So the focus is, okay, let's get out there and we can observe, because the noise is so low with just a 1 meter telescope. There can be some unprecedented observations of dark objects. There's a whole bunch of different types of dark objects, and one of them could include extrasolar objects that have been trapped in the Kuiper belt. So an extrasolar object comes close to the sun, and usually it flies straight back out. But if it interacts with Jupiter, it will actually get captured. So if you're observing and you're looking for these dark objects in the Kuiper belt, it's very likely to be extrasolar if it's in the Kuiper belt, not in the plane. When you get out to the Oort cloud, who knows what it is? There's a whole bunch of stuff in the Oort cloud. But in the Kuiper belt, just like New Horizons picked a secondary target. They flew past Pluto and said, oh, what do we fly past next? But because they were in the plane of the ecliptic, it was almost assuredly an object that formed in the solar system. But there might be Oumuamuas that are trapped in the Kuiper belt, and this would be a really strong architecture for developing a telescope that could detect these dark objects, because you're just really hard to see them in a near Earth kind of orientation, even if you have a giant, amazing telescope.
Yeah, there was a great observation made by New Horizons within the last couple of years that they did exactly this. They took its relatively small telescope and they just looked at space itself. And because it's away from all of this interplanetary dust, it was able to make observations and set some hard limits on like the structure of the cosmos, purely because it's just not obscured. It was not a large telescope, but because it was so far away from all of this solar system dust, at certain wavelengths, it was exactly the right machine. And there are some really interesting, I've done an interview about this, some really interesting like infrared observations that you want to make, some ultraviolet observations that you want to make that that dust is, as you say, sort of setting a lower limit on what it is that you can and can't see. So you're proposing to send a telescope out beyond, say, the orbit of Pluto and then start scanning the sky for dark objects, which could be trapped interstellar objects. And now that delta V nightmare mostly goes away because they're with us. And so now it's a matter of finding them and then tasking future missions to intercept them. Is that what you're suggesting?
That's part of it. I think I've got more.
Okay, I'm ready. Bring it.
So we're targeting. So there's a new innovation in the architecture, and this is actually just like a rocket has a first stage and a second stage, right? The first stage is a short-lived thing that you drop on your way, and your second stage, circularizes your orbit. Well, the same concept applies here with radioisotopes. So we actually have a even shorter half-life. So we have a two-stage radioisotope electric propulsion system now. So the first stage, shorter lived, and it allows you to get up to a boost speed of about 25 kilometers per second almost instantly. Because a lot of times with electric propulsion, it takes you a long time to accelerate to speed. But this would get you out of the gravity well pretty quick, out of the solar system's gravity well pretty quick. And then there's a second stage, which is an endurance stage with a separate radioisotope. And that can provide power, heat, and propulsion. And one of the big challenges is actually radio bandwidth. As you know, New Horizons had a lot of problems with, it took a long time to transfer all the data from its, really, an hour or two of a flyby for, months and months and months of bandwidth. So being able to power a radio in addition to your electric propulsion is enabling for science. And so with the science piece on top of what I talked about is, let's imagine, New Horizons was expressly built for one purpose. But what if you had a spacecraft that had a cruise stage and you have a budget of like 25 kilometers per second of delta V to do whatever you want with? You can decide on the fly. And one of the things could be, hey, we found an Oumuamua-like object. Let's actually intercept it, right? We can slow down and orbit it and observe it. Potentially, if you sacrifice another bit of payload, you might be able to still do your sample return from that. But they think, I've got some papers that I referenced in my proposal where they did an estimate of how many trapped Oumuamua-like objects are in the Kuiper Belt. And there's actually a lot.
Like 30,000 or something.
Yeah. So if you have enough delta V, you can probably find one and go poke at it, or find a bunch and figure out which one is the most interesting and what you have the delta V budget for. And oh wait, there's one more thing which is really cool we put into our proposal. So I know you've talked about gravitational microlensing on your program, and you've probably talked about parallax as well, measuring distances. And there's actually a way to combine gravitational microlensing, that's the effect where light bends in a strong gravity field. So if you observe, you can actually see behind an object or around an object, and you can infer certain things like mass from that object. But there are a lot of interesting objects that if you take a measurement from Earth and you take a measurement from several 10 AU, and you look at the gravitational microlensing, you can actually tell a lot more about the mass to much greater precision. And you're taking measurements along the way. And it can also, there's a whole bunch of objects, like, let's say, stellar mass, specifically black holes. So smallish black holes that we actually don't know a lot about. We don't know kind of exactly how many mass, like, they're kind of rare objects out there. We've only found a couple of them. And it would be really interesting to figure out, hey, what actually is the mass of these small black holes? Because we haven't been able to find a way to measure them separately. So gravitational microlensing parallax, a little bit of a mouthful to say, but that was actually the next, and kind of there's still more science you can do, but this proposal, what it does is the way we've proposed it is, hey, we have a science team composed of a couple strong scientists, including, as I mentioned, John Ehrenberg from the James Webb Telescope. And we have our technology team that's looking at the power source in the spacecraft. And what we're actually providing isn't just a single design, but a system design. Hey, you could have a larger payload, or you could have more power, or you could do this. Scientists, go work your magic, go figure out what is possible. Don't let me drive your mission for you as the technology. I'm going to tell you all about what my technology can do with these system and integrated models. And I want you to come up with interesting, new, cool science. And, there might even be more things that can be done that we haven't even thought of yet on the fly for the science piece.
Well, I mean, you've got to be familiar with the solar gravitational lens telescope concept from Dr. Slavoj Turyshev, another NIAC awardee. I think he's passed all the way through all three phases at this point. And he's looking for a 1 meter telescope deployed out to the solar gravitational lens between 500 and 1000 AU. If you can do that, then he figures you can get a 1 megapixel image of an extrasolar planet. So,
yeah, I'll pull up my calculator here, but I'll show you. There's a direct, when I talk about 100 kilometers per second, that's a certain number of AU per year, right? So that's about 21 AU per year. And what I will say is to get much over 100 kilometers per second is still pretty hard. So the solar gravitational lens at something like 600 AU, or
so it starts to kick in about 550.
So it's still, the challenge on that one is distance. So a lot of the things that I'm looking at because of the shorter half-life would actually run out of power-ish, but they would be able to give you that delta V boost to get out there. So that's kind of where it would still be useful for that type of mission. But I think traveling at 21 AU per year would take you 5 years per 100, take you about 25 years to get out there.
I think that's about the time frame that they're hoping for. And, at this point it's been fusion rockets. And then the big idea right now is solar sails, where you do an Oberth maneuver going past the sun. And so you just drop down with a solar sail and then go really close to the sun, and then hopefully that gives you a gigantic kick. But it sounds like it's just in the realm of what they would be looking for as well. So, I don't know, talk to Dr. Turyshev, and I'm sure he'll have a lot of ideas for you as well.
One of them that I did think on that was it actually takes a lot of delta V to drop into the sun. If you can, the Earth is traveling around the sun at 30 kilometers per second. And, so I was like, well, why don't we have a radioisotope propulsion system or it could be solar. You're close enough to the sun. You could use solar too, but, to kill that initial delta V. So that was kind of my take on how it could be beneficial. Or 25 years is right on the border of where we could look at slowing down. But I was asking the question, is it any use to slow down?
No.
And a lot of people told me no. No. Don't bother slowing down. We actually want to be traveling, and it can give us some interesting things. So I initially misunderstood the concept because I thought you wanted to be stationary, because my thought is that you wanted to focus on a planet. But some people have said, oh, well, you can still travel at a high speed in a straight line and get the resolution you want.
Once you hit the lens, then as long as you are able to stay in the cone, the ever sort of decreasing cone, you can stay in that lens forever. Like, go for light years if you want, and you're still providing value as a telescope. But there is another idea where you would fly out to almost the very edge, into the Kuiper belt, where your sideways velocity around the sun is almost zero. And then if you can hover, then you can kind of maintain position at a certain point above the sun, you've got very little gravity trying to pull you back down. You've also got very little sideways velocity. But I do think, if you sort of showed the math to any number of astronomers and goes like, is this interesting to you? They'll be like, yes, please. Yeah, I've got ideas. Have a seat. Let's talk about this. So you're just going to provide this gigantic engine. So what is the deliverable for phase 2 then? What are you hoping to accomplish with this round of development of the technology?
Yeah, so I mentioned the integrated system model, that I have in my mind a graph that shows, let's say, payload mass versus delta V, and a bunch of X's over in one spot that says, oh, these are some really cool science missions here, and a bunch of X's on another spot that says these are some cool science missions here. You're able to click on one of them and look at, hey, this is the spacecraft design that would be able to achieve that. And you would look at one stage where here's what we could achieve assuming some aggressive assumptions, but another one is, what's a stepping stone? How do we get there? So hopefully there's some maybe slightly lower performing missions, or easier to do, whether they be lower power or less radioisotope. And you can say, hey, for a phase 3, let's focus on a more fully fleshed out, either conceptual or, I've met many engineers who, when you say conceptual, preliminary, and detailed design, they have very different ideas of what you're talking about. But the idea is that you flesh out, like, what I want out of this study is a complete design space and all the cool science that goes with that design space. And if there was to be a next phase, it would be, hey, we've picked a spot that looks attractive and doable. Let's actually try to move towards that and build it and make it real.
I like this idea of having different RTGs for different parts of the mission. When we think about Curiosity and Perseverance and Voyagers, like, they just have this one chunk of decaying plutonium, 238, and it just does its job. But in fact, there are different isotopes of different elements with different properties, some which put out the heat faster, but they have a shorter half-life, others which are safer, others which can last longer. And it could very well be that you can mix and match your different stages of isotope engines to get you different kinds of missions. That would be sort of a really interesting future where someone is planning a mission. They're like, well, we're going to need a cruise stage, and we're going to need a kick stage, and then we're going to need a return stage. And each one is a different isotope, providing the different kind of power.
Yeah. I'll even say there's one, this is a little bit of a side tangent, but I've done a lot of trade studies looking into isotopes that we either procure or produce. But on Project Starshot, I always said, hey, plutonium-238 doesn't have a long enough half-life to get out to Alpha Centauri. There's actually some isotopes you can get a few thousand years out of. And so instead of that providing primary propulsion power, all you're really trying to do is get a few milliwatts out so that when you get there, you can transmit your signal back to Earth. And there's just, every isotope has its killer application, what it does well. NASA selected plutonium because they were looking at, I need multiple decades. I want to go into the outer solar system. I want them to be minimally intrusive, right? So but initially in the 1960s, they actually were looking at 4 or 5 different isotopes, including cobalt, including strontium, including polonium. But there were decisions made, we need to select one, and that's the one we're going to look at. And when we get to the other NIAC that we're going to talk about, I'm going to talk to you about how that's, there's another idea of, here's a different way to look at it where you don't end up with the optimal solution being what NASA has chosen.
Yeah. All right. Well, we're going to get into that then as part 2 of this conversation. You can get even more space news in my weekly email newsletter. I send it out every Friday to more than 60,000 people. I write every word. There are no ads, and it's absolutely free. Subscribe at university.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at university.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent and keeps ads at a bare minimum. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Paul Davis, Vlad Shipolin, Jay Dennis, David Giltonen, Modso, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verabioff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. All your support means the universe to us.